Thank you very much, Evgenios, for the very kind introduction. Well, it's a pleasure to be here virtually via Zoom. So one of the nice things about the current situation, there aren't many nice things, but one of the nice things is being able to talk to audiences I wouldn't normally get to speak to. The downside is that anyone can join, and so I've got quite an intimidating participant list here, but there we go. Okay, so as Evgenios said, I sort of work in quantum groups mostly these days, but I have this, I did my PhD in Banach algebras, and I have an ongoing sort of lifelong interest in thinking about general Banach algebras and comparing and contrasting them to C-star algebras. And often, well, Banach algebras are much more general objects, and there's much less theory. So what I'm going to talk about today is particularly interested in classification of idempotents or projections, and in particular, I'm going to spend some time motivating the ultrapower construction. And I'm going to assume that some or much of this is new to at least some of the audience. So I'm going to try and go quite slowly, and I apologize to some of the experts who probably know most of what I'm going to say. Okay, so I want to motivate ultrafilters. So from elementary analysis, I've just been teaching that this year, we know that compactness is equivalent to every sequence having a convergent subsequence. So for example, if I take the sequence 1, 2, 1, 2, 1, 2, 1, 2, well, I can pick a subsequence which converges to 1, or I can pick a subsequence that converges to 2. Okay, completely obvious. Here's a more complicated sequence bouncing between 3 and 4. Again, I can pick a subsequence that converges to 3, or one that converges to 4. How do I choose which subsequence I'm going to pick? Well, why would I care which one I choose? Well, for example, if I add up these two sequences pointwise, I get this more complicated sequence. And what I quite like is that if I chose 2 here, and I chose that this one should converge to 3, then whatever I'm using to make my choice should surely choose 5 as being the limit of this one. So how can I consistently decide which subsequence I'm going to pick so that, for example, this adding up thing works for me? And the answer to that is an idea that comes from set theory, although it's not really set theory. It is this notion of a filter. So a filter is simply a collection of subsets which satisfies these rules. If I've got 2 sets in my filter, then the intersection is still in my filter. If a set is in my filter and I have another set B that's a bit bigger, then B is in my filter, and I'm not going to allow the empty set to be in my filter. So this ensures that I haven't simply chosen everything. And the way of thinking about this is that the subsets of my filter are big. So obviously axiom 2 makes sense. If I make my set bigger, it should still be in the filter. And axiom 1 is just saying that if I intersect 2 big sets, I still have a big set. And what we're going to do is we're going to use filters to make this choice for us. An example of a filter is the fresh shape filter. That's the collection of all cofactor sets. A set is in the filter exactly when the complement of that set. Sorry, I should have said I can see the chat. Have questions. Type questions. Okay. There you go. Okay, I'll carry on. So I'm going to define for an arbitrary filter, a sequence converges along that filter if, to a limit point A, if for any epsilon, the collection of indices n, where the sequence is close to A, is in my filter. Okay, so we don't want to look at just arbitrary filters. We want to look at things called ultrafilters. So the collection of filters on a set I is partially ordered by inclusion. If I have a filter, I can talk about one filter being contained in another. And if you play about with Zorn's lemma, it's quite easy to show that there are maximal filters. Every ascending chain has an upper bound, so I can use Zorn's lemma. And maximal filters are called ultrafilters. And if you've ever seen these things before, you'll know the following lemma. And this says that I can characterize ultrafilters as being those filters U such that for any set, either the set is in the filter or the complement of the set is in the filter. So in ultrafilter, every set, either the set itself is big or the complement of that set is big. So it's kind of making somehow a maximal choice. So what's an example of an ultrafilter? Well, a cheap example is if I pick some point in my set, and then I look at all of the sets which contain that one point, where you can check that that is a filter and it satisfies this lemma, the condition of this lemma. But these are not very interesting. We call these principal ultrafilters. How might I construct a more interesting example? Well, I can use Zorn's lemma. If I start with the Frechet filter and then find a maximal filter which contains the Frechet filter, then that will be an ultrafilter because it's maximal, and you can check easily it won't be principal because the Frechet filter is not principal. And there are loads and loads of these things. So there are lots and lots of non-principal filters. So if I fix an ultrafilter, then you can use and it's going to do that in a consistent way. So for example, we have the following nice result. If I have two bounded sequences, if I add them up pointwise and then take the limit along the ultrafilter, that's the same as taking the limits and adding them up. So this is exactly the condition I was worried about earlier. So that's all very well if I'm just interested in the real numbers, but suppose I'm interested in something like a Banach space where I don't have a good notion of compactness. How might I deal with this idea of trying to force convergence? Because not every sequence every bounded sequence is going to converge because I don't have compactness. And the slightly vague idea is that we're going to enlarge the space that we work on using the ultrafilter. So to be a bit more precise, it's the ultrapower construction, which I'm not going to try and explain. So given the Banach space E, let's let L infinity E be the space of all bounded sequences with pointwise operations and the supremum norm. So for any filter, I'm going to define N of F to be those sequences in L infinity of E, such that if I look at the norms of the sequence, so that's just a scalar now, I want the limit along the filter of those norms to be 0. And remember, that's what it means, that the limit is 0. So it's easy to check that this is a subspace. It's obviously closed under scalar multiplication. It's closed under addition because the filter is closed under intersection. Perhaps slightly more surprising is that this subspace is closed. You would think, or at least I thought, maybe I'd need some condition on the filter, but actually it's always closed. You just copy the uniform convergence argument that shows that L infinity of E is a Banach space. So this thing's always a closed subspace, so I can always form the quotient space. And that's what I call I forget the correct name for these things, but when F is an ultrafilter, this is the ultrapower. Okay, so if I pick a non-principal ultrafilter, the ultrapower of the Banach space is this quotient by L infinity of E by the sequences. Thanks, Spencer. It's the reduced product. So it's the quotient of L infinity of E by the null sequences for the ultrafilter. Now, when I'm in the special case of an ultrafilter, I can make an alternative definition. I can define a semi-norm on L infinity of E by this description. So if I look at a sequence xn, if I look at the norms, that's now a bounded sequence of real numbers. And so I can always find the limit down the ultrafilter because I have an ultrafilter. So that's going to give me a semi-norm. It's going to send lots of things to 0. And in fact, the things it sends to 0 is exactly this null space n. So I can think of the ultra power as simply being L infinity V with this semi-norm, while I then quotient it out by the things that are 0 for that semi-norm. So that's quite nice. That allows me to confuse elements of my ultra power with elements of L infinity V, with bounded sequences. And of course, I just have to remember whenever I try and define something here, I have to check it's well defined. And then finally, there's always a map from my original space into the ultra power. I just send an element x to the sequence which is constantly x. And then because then if xn is constant, this limit is constant. So this map is seen to be an isometry. And we might think, well, perhaps I've done nothing. Perhaps this map is always a surjection. Well, that's true if and only if my space is finite dimensional. So if my space is finite dimensional, then the unit ball is compact, and so I can take the limit of any sequence in the space. And that shows that in the ultra filter, in the ultra power, any sequence is equivalent to the sequence which is just constantly equal to its limit. So in other words, this map is surjection. But as soon as we're infinite dimensional, I can find sequences that don't converge, and then this ultra power is much bigger than the original space. And the rough intuition I want to have is that this ultra power is sort of allowing me to think about the limit of xn is just the element of the ultra power that the sequence xn defines. So I'm sort of introducing a whole load of more limits by making my space bigger. And I think that's a bit of a vague intuition, but it's perhaps not completely lying. Okay, so to think about these things a little bit more, let's look at some examples. So I suppose what's the ultra power of a Hilbert space look like? Well, if H is a Hilbert space, I can do something nice on the ultra power. I can form a sesquilinear form. So if I take two elements, an and bn, in my ultra power, I'm going to take the inner product of them will be, well, just take the inner product for each n. That's now a sequence of complex numbers. It's going to be bounded because the sequences a and a b are bounded. So I can take the limit along the ultra filter. Well, why is that well defined? Because remember, this is not really sequences, it's equivalence classes of sequences. Well, if I happen to pick a sequence which was really equal to 0 in the quotient, well, what does that mean? Well, that means that the norms tend to 0 along the ultra filter. Well, then that means if I take the inner product of any bn, I'm going to get limit of 0 just from the Cauchy-Schwarz inequality. This thing will be at most norm of an times norm of bn. Norm of bn's bounded, norm of an's going to 0. Well, then this goes to 0. So this is well defined. It's clearly sesquilinear. It obviously recovers the original norm I had on the ultra power. Again, I guess there I'm using that taking the square root commutes with an ultra filter limit, but it does. So this thing is a Hilbert space. It's a Banach space that whose norm comes from an inner product. So it's a Hilbert space. And this gives us a bit of motivation for why I want to work with ultra powers and not just reduced products. If I used another filter, I wouldn't necessarily get a Hilbert space out of this construction. So for example, if I use the Frechet filter, that's equivalent to quotienting by sequences which in the usual sense tend to 0. So my reduced product in that case would just be quotienting by C0 of H. And that's not a Hilbert space. There's no inner product on this quotient that gives me the norm. So ultra powers are quite nice because they preserve a lot of the structure that we're interested in. So a couple more examples of that phenomenon is, suppose I start with a Banach algebra and I form the ultra power of that. Well, I can define a product by just doing stuff pointwise. And again, you check that's well defined. If I change an to something it's equivalent to, I change the product to something that's still equivalent. If I happen to start with a C-star algebra, then I can define an involution just by doing it pointwise. And that's going to satisfy the C-star condition. So I see that an ultra power of a Banach algebra is again a Banach algebra, an ultra power of a C-star algebra is again a C-star algebra. And a nice link with the previous slide is that if my C-star algebra is represented on the Hilbert space H, then naturally the ultra power of the C-star algebra is represented on an ultra power of that Hilbert space. So I guess maybe some people in the audience are interested in von Neumann algebras. Notice if I started with a von Neumann algebra, the ultra power will be a C-star algebra, but it won't necessarily be a dual space. So that's where stuff breaks down. The ultra power of a von Neumann algebra is not a von Neumann algebra. But this idea of the fact that there's a natural representation on a Hilbert space gives you at least one way that you can think about constructing something like an ultra power of a von Neumann algebra. You form the C-star algebra, you represent it on the Hilbert space, and then you take double commutant. And there's other constructions in the literature. Okay, so this is so I'm now going to talk about stuff that's new or vaguely new. So this is all work with Bence Horvath, who's in the audience. So Bence is a postdoc in Czech Republic in Prague, and it's been really fun working with him on these questions. So let's suppose we fix a Banach algebra A, and we ask the following question: when is an ultra power of that algebra unital? Well, if the algebra I started with is unital, then I always have this diagonal embedding of the original algebra into the ultra power, and then the unit for the original algebra is really easy to see that that's still going to be a unit for my ultra power, so my ultra power is unital. Well, what about the converse? Is perhaps the converse true? Well, let's have a go at trying to prove that. So let's pick a unit for my ultra power. Well, this has a representative in L infinity of A, En. And what does it mean that it's the identity for the ultra power? Well, that means if I multiply it by any sequence An, then I don't just get An back, but I do get in the limit An. So in other words, En times An minus An should go to 0 as n tends along the ultra power. Sorry, the ultra filter. And similarly, it's meant to be a two-sided unit, so the other way around as well. And for the rest of the proof, I don't want to have to worry about the ultra filter. So let's just pretend this was normal convergence, just to make life a bit easier. So these sequences are tending to 0 for any bounded sequence An. Well, that means that I can show the following, for example. So if I look at this, then for each n, I'm going to pick An of norm 1 that almost maximizes the error I get here. And then I make the approximation better and better as n gets bigger. So this allows me to show that the limit in n of this supremum is equal to 0. So these ENs are somehow getting better and better at not moving A very far from A. So that's what we showed, and I have the same thing on the other side. Well, what am I going to do with this? Well, this convergence might be happening quite slowly, so let's just extract a subsequence so that the convergence is happening at least at 1 upon n speed. I also know that all of my ENs are bounded. Let's just say they're all smaller than k. So let's look at what the difference between En and Em is. Well, let's use this second one applied to Em. So En is, so this will be smaller than k times 1 upon m. And this one applied to En here, so A is now going to be Em, will give me k 1 upon n. But that means this thing's a Cauchy sequence. If I take n and m large, this is going to be very small. So En is Cauchy, but of course my Banach algebra is complete, so it converges, say, to E. So that was all with normal convergence, where you can do the same thing with ultrafilters. You just have to do a bit more bookkeeping, but the same argument works. So a ultra power is unital if and only if the original algebra is unital. But somehow that proof was not at least to me, completely trivial. We seem to have to do some sort of effort there. So I want to very quickly make some links with metric model theory. So I'm not a model theorist, but sort of Benson and I learned a bit when we were doing this. So there's a way to study metric objects like Banach algebras from the perspective of model theory. So model theory is a branch of mathematical logic. It's interested in language of structures. So the language we have to use here has to take account of uniform continuity. And we're not going to think about things being true or false. We're going to think about things taking us a sort of continuous valued version of logic. So we can't talk about a statement being true or false, but we can talk about its value being something between 0 and 1. Its convention, maybe we choose 1 as being true and 0 as being false. And similarly, I can't talk about the normal exist and for all quantifiers. We use supremum and infimum in their place. So that's all incredibly vague. If you know a bit about model theory, hopefully it slightly makes sense. There's a notion of ultrapower in model theory, which also works in this metric model theory, and it agrees with our definition. And there's a version of the famous Wash's theorem, which tells us that a formula holds in a structure if and only if it holds in an ultrapower. So on the face of it, this would be an incredibly useful result for us, because if I can express something as a formula, then this theorem immediately tells me that I don't get anything new if I look at an ultrapower. The downside is that I'm not allowed to use exist and for all. So if I'm expressing some formula, I have to use sup and inth and other sort of continuity flavored things. So the tricky bit is, how do I axiomatize the properties I'm interested in? So for example, here is a way to axiomatize that a Banach algebra is unital. And that should look very familiar from the argument I just gave you. And it looks nothing like how you would normally write down the axiom for being a unit. But the normal way you'd write down the axiom for being a unit would be there exists something such that for all something, something is true. And I'm not allowed to do that. And this is the way out of that. So this is saying that I can sort of the infimum over any choice of possible unit should, oh, sorry, I haven't told you what B1 is. B1 is the closed unit ball. So the infimum over possible units times the supremum of things in the unit ball, the possible unit should not be very far away from being an actual unit. And then the argument we gave about extracting a Cauchy sequence exactly shows that this really is equivalent. So for at least to me, the moral of this is that the hard work is in using the model theory setup to axiomatize the things you're interested in. So I'm not going to say anything more about model theory, but if people know about ultrapowers, that's a natural thing to talk about. Okay, so what I really want to talk about is idempotence and equivalence. So given a Banach algebra A, an idempotent is just something that squares to itself. And I'm going to say that two idempotents are equivalent if there are two elements in my algebra. I multiply them one way around, I get one idempotent. I multiply them the other way around, I get the other idempotent. And I always think it's nice to have a little lemma to prove in a talk. So you might want to prove, why is this an equivalence relation? Well, I've written down there, but I'm not going to go through it. This is an equivalence relation. It's not entirely obvious when you first see it that that it's transitive. So let's think about an example. Let's look at n by n matrices, which I can think of being the linear maps on C to the n. Well, then an idempotent corresponds to a direct sum, a way to write C to the n as one vector subspace, direct sum, another vector subspace. The image of my idempotent will be one space, and the kernel of my idempotent will be the other space. And then equivalence exactly looks at the dimension of the image. So if I've got two idempotents and they have the same dimension of the image, then they're equivalent in this sense, and that's the only way they can be equivalent. So again, that's a nice little exercise to go away and think about. Okay, so I think most of the audience is, oh, sorry. So I just want to talk about finiteness. So an algebra is Dedekind finite if whenever an idempotent is equivalent to the identity, then already the idempotent is equal to the identity. So matrices are Dedekind finite because of dimension. If an idempotent is equivalent to the identity, then the image of that idempotent must have full dimension, must have rank n, but then it has to be the whole space. So the idempotent actually has to be the identity. What's an example of a Banach algebra that's not finite? Well, something like the bounded linear operators on a classical sequence space is not finite because there are proper subspaces that are isomorphic to LP. So I can find a projection onto a proper subspace. It's isomorphic to LP, that subspace, so the projection will be equivalent to the identity, but of course that projection is proper, so it's not equal to the identity. Okay, so what I thought was the next slide is this one. So for C-star algebras, probably you don't think about projections, idempotents, probably you think about projections. So for a C-star algebra, we typically only think of self-adjoint idempotents. And then the normal equivalence to consider is that of Murray von Neumann equivalence, where instead of arbitrary elements doing the work for me, I need a partial isometry. So this is the same idea. I've got two elements and I multiply them in different orders and I get my two projections, but now I have a partial isometry. Well, actually, these concepts aren't really different. So given any idempotent in a C-star algebra, there's always a projection that's equivalent to it. So you can find non-self-adjoint idempotents, fairly obviously, but I never get anything different if I just look at equivalence classes. And if I happen to start with two projections, then you can show that they're equivalent in the sort of algebraic sense. Well, that implies that they're equivalent in the Murray von Neumann sense. The converse is obvious. So this is not really a different notion of equivalence, even though it looks it. And then, for example, if I have a Dedekind finite C-star algebra, and then I pick some idempotent, not necessarily self-adjoint, that's equivalent to 1. Well, then there's some projection equivalent to my P, but then by transitivity, that projection is equivalent to 1. By this second bullet point, it's Murray von Neumann equivalent to 1. So by the assumption of Dedekind finiteness, it's equal to 1. But then we play with some of our formulae, and then we see that our original idempotent already had to be 1. So a Dedekind finite C-star algebra is also Dedekind finite in our formally stronger sense. So we don't actually get anything new. Okay, so a couple of other things we can do with idempotents. An algebra is properly infinite if there are two idempotents, both equivalent to 1, which are orthogonal. In this sense. So that's kind of a very strong form of not being finite. Okay, if I was finite, then P and Q would both have to be 1, and then obviously they couldn't possibly be orthogonal. So for an example, again, bounded linear maps on a classical sequence space is properly infinite because I can find two sort of orthogonal, whatever that means, subspaces that are isomorphic to LP. And in a C-star algebra, again, if I just work with projections, I don't get anything new. And then these things are really very classically studied for simple unital C-star algebras. And in that setting, you can prove lots of nice results. So here's one. I don't know who to attribute this to. I guess this is sort of classical result by now. So suppose I have a simple unital C-star algebra. Well, the following is infinite. A is infinite. That is not Dedekind finite. Well, that's equivalent to A being properly infinite. And that's equivalent to there being a left invertible element, which is not invertible. So we sort of get quite a lot of structure for free, and sort of C-star algebras that satisfy these or my next condition are very well studied. So the condition, so Benzer and I looked at these properties and how they're preserved under the ultrapower construction a couple of years ago now. And then more recently, we've been looking at a further stronger property that we couldn't make any progress with for quite some time. So an algebra is purely infinite if A is not just the complex numbers, and for any non-zero element, I can find some other elements, B and C, such that BAC is equal to 1. So, okay, that's a definition. It's not very hard to make sense of. It seems to have nothing at all to do with idempotence. So what's going on? Well, here's a theorem that's stated just in the algebra case. So suppose A is a simple algebra. Well, the following are equivalent. A is purely infinite in this sense. Every non-zero right ideal contains an infinite idempotent. So it's somehow equivalent to there being lots and lots of infinite idempotents about. And in a C-star algebra, these things are again very well studied. Again, I don't know who to attribute this to. It's probably a sort of fairly classical result by now. So if I have a C-star algebra, equivalently, every non-zero hereditary C-star subalgebra contains an infinite projection. So it's somehow a very, I guess the purely infinite bit comes from the fact that, well, I think the language comes from von Neumann algebras, where you have a sort of decomposition theory. But a way to think of it is that if you're chopping your algebra into ideals or into hereditary subalgebras, they sort of stay infinite. Okay, so we want to think about when are ultrapowers purely infinite? And motivated by Walsh's theorem and previous work, having norm control is really important. So to be purely infinite, what I need to do is for any non-zero A, I need to solve this equation. I need to find B and C such that BAC is equal to 1. And what I want to do is measure how some sort of norm control over this. So what I'm going to do is think about what's the infimum of the norm of B times the norm of C for B and C that satisfy this. So it's somehow getting some sort of metric quantity associated with being purely infinite. So an algebra is purely infinite if this constant is less than infinity for each A. But of course, if I choose a different A, maybe I get a different constant. And we always have some simple inequalities. So I always have that this thing is bigger than 1 upon the norm of A, and it's homogeneous in a slightly complicated way. If I scale my element A, then if A is getting bigger, I can obviously make B and C smaller and still satisfy this. And so if I scale A by Z, then I scale the constant by Z inverse. So this suggests that I only need to look at the unit ball to understand what this thing is doing. So for unit Urbanic algebra, the following are equivalent. An ultrapower is purely infinite. This constant is uniformly bounded on the unit ball. So let's think about why this might be true. So 2 implies 1 is not so hard. If you write down what you want to do, it sort of becomes natural to look at this. Let's think about proving 1 implies 2. Well, let's use contrapositive. So if this isn't true, there's a sequence in the unit ball with this constant going to infinity. Well, let's let AN define an element of the ultrapower. And then within the ultrapower, I can solve my equation BAC equals 1. So let's pick representatives for B and C. Well, BAC equals 1 in the ultrapower means exactly that BN, AN, CN convert, well, gets close to 1 in the ultrafilter limit. Well, if these things are getting closer and closer to the identity, that means that for n large with respect to the ultrafilter, this element is invertible because it's close to the identity, and its inverse is not going to be very large. Well, that means that I can then multiply by the inverse on one side and exactly solve my equation. So that tells me that this constant, this purely infinite constant for the AN is going to be controlled by some constant times the norm of B times the norm of C. But that's true for any n, because B and C aren't changing. So that contradicts my assumption. So somehow and this ties with previous results that we had. So things being purely properties preserving with the ultra power construction often have some sort of metric control behind them. So what are some applications of this? Well, immediately we see that if an ultra power is purely infinite, then I have uniform control over these constant. Well, in particular, this constant's always finite. So in particular, my original algebra was purely infinite. What about the converse? Well, let's think of some examples. If I have a simple unit of purely infinite C-star algebra, then my constant is as good as it can be for everything in the unit ball. So again, this is a classical result. You look up a textbook on C-star algebras about purely infinite case, and you can extract a proof of this result really quickly. It's using positivity, functional calculus, normal sort of tools. For a more Banach algebraic example, I'm going to look at Banach spaces. So let B of E be the algebra of all bounded linear operators on E. Let K of E be the algebra of compact operators on E. Now, for some nice spaces E, the compact operators form the unique closed two-sided ideal in the algebra of all bounded operators. And so this quotient, sort of generalization of the Calkin algebra, turns out to be simple. In particular, that's the case of C0 or LP, the classical sequence spaces. So this algebra is simple, and it turns out not only that it's purely infinite, and not only that it has purely infinite ultrapowers. Well, again, what you do is you know the correct place to go and look. So this is a result of Ware, who's a PhD student in Australia. You go and look at his thesis. He's interested in proving different things about this algebra, but one of his results translated into our language exactly gives this estimate. So if I have a non-compact T, then that T in this quotient algebra gives me this constant is exactly the best it can be. So I can, what you do is you sort of extract a subspace of the image of T that is extremely close to being isometric to the original space you started with. So the generalization of the Calkin algebras have purely infinite ultrapowers. So what we wanted to do is to think, well, surely it's not the case that every Banach algebra that's purely infinite has metric control of this thing. Banach algebras don't have metric control. So we're going to look for a counterexample. We want a Banach algebra which is purely infinite, but we have no good control of this constant. How am I going to do that? Well, that's hard because being purely infinite is a global property. It says for every non-zero A, there are B and C such that. So I can't just play games with fiddling with the norm or anything like that, because any way I have of taking an example and changing it seems to destroy this global property. So the way we're going to get at it is rather it's rather roundabout, and it's going to use this result. So let A and B be unital Banach algebras. If A has purely infinite ultrapowers, then any homomorphism from A to any other unital Banach algebra is automatically bounded below. So that should look familiar from C-star algebra theory. We, of course, never have this for general Banach algebras. But if I'm purely infinite, if I have purely infinite ultrapowers, then I do. I don't want to spend too long on the proof, but basically, if I can solve BAC equals 1, I can also solve that in the image of B, just by pushing forwards in my homomorphism. So if theta of A has gotten really small, but this is still true, theta of B and theta of C must be large, but theta's bounded. So that means B and C must have been large. And that means that I can't then have control on this. Or conversely, if I do have control on this constant, then theta of A can't get too small. Okay, so The way we're going to construct an example is the following. So I'm going to talk about the Kunz monoid. It's often called Kunz semigroup, but that rather has a different meaning in C-star algebra theory these days. So this is so it's a semigroup given by generators and relations. So it's got 4 generators, S1, S2, T1, T2. If I multiply them together in sort of the correct way, T1, S1 gives me the identity. If I multiply them together in the wrong way, T1, S2 or T2, S1, that gives me this weird angular 0. And this thing is a semigroup 0. It's something which absorbs any other element of my semigroup into itself. So this semigroup is all the words in these generators subject to the relations. So I just did 2 examples here. Let's look at this word. Well, buried in here is T2S1. That equals this weird 0. So I can replace that by the 0, but then the 0 absorbs everything and I just end up with 0. In this one, I've changed it so I have T2S2. That's equal to the identity, so I can just cancel that out, and then I get this. And if you stare hard at this, you'll realize there's no further cancellation. And in fact, any word you write down either reduces to 0, or you end up with a word like this that starts in S1, S2, perhaps repeated in lots of different orders, and then ends in T1 and T2. Because every time you have a T occurring to the left of an S, the T will either cancel out to give me 1 or cancel out to give me 0. Okay, so that's a semigroup, or it's a unital semigroup, so it's a monoid. How can I find one algebra? Well, there's a standard way in Banach algebras. We look at the L1 construction. So I'm going to look at all sequences indexed by my semigroup with finite L1 norm. So if I add up all of my absolute values, I have something finite. So I'm going to think of this as being formal sums where I have a point mass at each element of my semigroup, and then I multiply that point mass by a scalar. And then how do I multiply 2 point masses? Well, I just use the semigroup product. And then let's notice that the span of the point mass at the 0 is a 2-sided ideal, because if I multiply it by anything, the 0 just absorbs it. So I can quotient out by it. It's a closed 2-sided ideal, and that's going to be my algebra A that I talk about for the rest of the talk. And notice that that's simply the same as identifying that point mass with the algebra 0. So for example, if I multiply T1 by S1, I get 1 in the algebra. If I multiply T1 by S2, I just get 0 in the algebra. Okay, so this, your people in C-star algebra theory probably recognize the Kunz algebra by this point. So the Kunz algebra is the C-star algebra generated by isometries S1 and S2. So that means that S1 star times S1 is the identity. And subject to this relation, that if these are isometries, then this is going to be a projection. And these 2 projections added together should give me the identity. Well, this in particular implies that these things have orthogonal ranges. And so S1 star times S2 will be 0, and S2 star times S1 will be 0. And so these and these relations should look exactly the same as what I had, except now T1 is just the adjoint of S1. So how do we, but in our case, because we started with a semigroup, we have nothing that corresponds to this axiom. So how can we introduce something that looks like this? Well, let's let J be the closed ideal in my algebra A that's generated by this element. So what does that mean? Well, that means that in the quotient algebra, if I add up S1T1 and S2T2, that's exactly equal to 1 in the quotient algebra. And J is the smallest quotient that would force this to happen. Okay, so what we're going to prove is that this quotient is actually a simple algebra. And we're obviously going to prove something about purely infiniteness along the way. Okay, so I looked before, I had this idea about homomorphisms. So I want to define a representation of my algebra. So let's just think of the Banach space L1 with standard unit vector basis En. And let's define some isometries, S1 and S2. S1 just sends E1 to E2, E2 to E4, so it sort of pushes onto the even bits, and S2 sort of pushes onto the odd bits, and then T1 and T2 sort of undo that. So T1 sends En to be En upon 2 if n were even, and it just kills it if n is odd. And these operators are set up so exactly I have these relations, which are the relations I had before. So T1, S1, well, T1 just undoes what S1 does, so that's the identity. T1, S2, well, S2 pushes everything onto the odds. T1 kills everything that's odd. So that just gives me 0. Furthermore, T1 times S1, that's projection onto the things supported on the even coordinates. And S2, T2 is projection onto things supported on the odd coordinates. So if I add those things together, I get 1. So I end up with a representation which annihilates my ideal. So that drops to a representation of the quotient. And it turns out that representation is not bounded below. I'm slightly running out of time, so I think I will skip the proof. But we see here, this is part of our construction, right? I've built myself a representation that's not bounded below. So this algebra cannot have purely infinite ultrapowers. However, the algebra is purely infinite. The proof is a careful but direct construction. Given any A in the algebra that's not in the ideal, so it's non-zero in the quotient, I can solve this equation. Let me just very quickly say that identifying the annihilator of my ideal and using Hahn-Banach turns out to be useful. How long do I have, Evgenios? Should I finish quickly or?
I think you should take your time to finish the proof.
Okay.
I'm interested in seeing it in detail, so I apologize to the participants.
Okay, let me just give a slight indication. Suppose I pick the generating element of J. So this is something for which my argument's not going to work with. I want to give an indication of why it doesn't work. So suppose I multiply A on the left by T1. Well, then I get identity times T1 gives me T1. I have T1, S1, T1, T1, S2, T2. Well, this is a T1, S2, so that's 0. T1, S1 is the identity, so this just becomes T1, but that cancels out with that to give me 0. Similarly, multiply by T2 gives me 0. Multiplying by S on the other side gives me 0. So if I'm trying to multiply, if I'm trying to solve BAC equals 1, then I can't multiply on the left by T, and I can't multiply on the right by an S. So I can only left multiply by S's and right multiply by T's. And then if you look at this, that's just going to give me longer and longer words. And I'm never going to be able to get the identity back. So that gives you some indication of why you can't solve this equation for something in J. And then you sort of play about with that and you notice that this is really the only obstruction. So something that's not in J, you can solve this. Okay, so A upon J is simple because it's purely infinite, doesn't have purely infinite ultrapowers because we constructed a homomorphism that wasn't bounded below. And what's interesting to me is that the example is quite natural. At no point did I come up with some funny norm. I didn't sort of put some weights in to sort of force things to behave as they were. Rather, it sort of fell out a bit by accident that we didn't have good norm control. Okay, so let me just finish by giving some references. So both our papers are on the archive. First paper's published in the Canadian Journal. If you're interested in the model theory aspects, there's quite a lot of work recently in this, but I think a nice place to start is by Fowler, Hart, and Sherman have a series of papers of roughly this title, Model Theory of Operator Algebras, which are really readable. And then I should say that this interest in sort of analogues of C-star algebras, Chris Phillips and collaborators have been doing a lot of work on this in the last 5 to 10 years. And Phillips studied in particular the closure of A upon J in B of L1 for exactly our map. And he showed that this is also purely infinite. And in some ways, the closure is similar to a C-star algebra. It's more similar to a C-star algebra than our algebra is. His proof techniques are completely different. And seemingly, we tried and we couldn't see how to adapt his proofs to our setting. What's going on is seemingly this. Suppose I have a homomorphism with dense range. There seems to be no relationship between A being purely infinite and B being purely infinite for Banach algebras. So there's kind of no logical relationship between Phillips's result and ours, despite the fact that we're almost studying the same algebra. It's just a closure. But I guess we know as analysts that closure can do a lot. Okay, that's all I wanted to say. I'm sorry for running over by a couple of minutes. Thanks again for the invitation to speak.
Thank you, Matt.